Hi folks, and welcome to the next session of the final exam review for Calculus 3208. In this session we're going to look at more limits and continuity business, and more specifically we're talking about how we compute limits, and underneath that general heading today we're looking at using a factoring strategy as a way to evaluate some limits that we wouldn't otherwise be able to tackle. Okay, so let's move along. We'll get started. So real quickly, we've got a couple of key topics we're going to look at. The first one is limits resulting in indeterminate forms from direct substitution. So when we fill in, it doesn't work, as we said, or as we should know from some previous study, that doesn't mean that the limit doesn't exist. It just means we might have to try something different. So one of those different things we can try to make it work is factoring and cancellation to allow for limit evaluation. Okay? So let's move right along and give this a whirl. So the first one says factoring to evaluate limits. Okay, so let's consider the function that's given, and the function that's given here says x squared minus 9 over x minus 3, and we want to evaluate that limit when x is approaching 3. Okay, so let's try that now. When x is approaching 3 here, well, if we try direct substitution on limit as x approaches 3, we're going to have x squared minus 9 over x minus 3, and that will give us 3 squared minus 9 over 3 minus 3, which is 9 minus 9 over 3 minus 3, and that is 0 over 0, and that is indeterminate. So we cannot evaluate that limit right there. So we have to try something else to see if we can get somewhere with this. So the next method that we're going to try, or the first strategy we're going to learn, is called factoring, which is something we all know well. So what we do is we take the expression inside our limit here, and we can factor our numerator, x squared minus 9, because it's simply a difference of 2 squares. So x minus 3 by x plus 3, all divided by x minus 3. And so what happens then is the x minus 3's can divide out to give us 1 over 1, and essentially what we have left is to evaluate the limit as x approaches 3 of just x plus 3. And now if we apply direct substitution, we get 3 plus 3, which gives us a grand total of 6, and that is actually the value of the limit. Now, anybody who's a little bit keen on this stuff is going to ask, well, how come I'm allowed to do that? What's going on here? Because isn't 3 a non-permissible value? And why is it that when it comes to limits, I'm allowed to ignore that non-permissible value? Well, let's clarify some of that a little bit. So what we get, if we look at the graph of the function that we started with, x squared minus 9 over x minus 3, right over here, this is kind of a different kind of a function. It's a function that looks like a rational function, but because of those factors that canceled out that we saw already, what we end up with is a graph that looks just like the graph of y equals x plus 3, except we've got this spot right here. And that spot is a little hole in the graph. Technically, we don't call that a hole in the graph. We call it one of two things. It's either a point discontinuity, or it's one category of removable discontinuity. But ignoring all those funny words, we're going to get into all that stuff in a later section. Why is it that we're okay with that? Well, let's think about what all this means. If we go back over here and we look at our equation for a second, and we simplify it like we did previously, x minus 3, x plus 3, all divided by x minus 3. And then we reduce that. We say that the function is actually equal to x plus 3 as long as x is not allowed to be 3. And it's this non-permissible value that we have right there that created that hole in the graph. So really, we can evaluate the limit for x plus 3 instead of for what we had in the beginning, as long as in the process of evaluating that limit, we never let x actually equal to 3. And what we remember is that from the definition of a limit that we've already seen, the only condition we have for it to exist is that as we approach a from the left, And as we approach a from the right, and of course in this case our value of a would be that 3, we get the same number. And so on this graph, as long as I'm approaching 3 from the left and approaching 3 from the right and getting that number 6 for y, it doesn't matter if I ever get there. In fact, by the technical definition of a limit, I'm never even allowed to think about being equal to 3. So as long as we're approaching and everything is okay, that actual getting there is not a big deal. So it's okay to do that. The non-permissible value doesn't hurt the value of the limit. So let's move on and try a few examples now. So first thing we should always try to do when evaluating the limit of any function is check direct substitution first. So if we try direct substitution here, we're going to get 2 squared minus 3 times 2 plus 2 all over 2 squared minus 2 minus 2. So it doesn't really matter about what's up top in our denominator, but what we get up here is 4 minus 6 plus 2, which is 0, and in our denominator on the bottom we get 4 minus 4, which is also 0. So numerator 0, denominator 0, by our limit rules, that is an indeterminate form, so that's no good. So let's try our factoring strategy now. So we're going to take the limit as x approaches 2. Up top we're going to have x minus 2 times x minus 1, and then the denominator we've got x minus 2 times x plus 1. We can see that we can reduce these factors, and we're not really concerned about that particular point because that point is at x equals 2 if we're talking about it as a non-permissible value, and we're not allowed to touch 2 anyway by this limit. So what that gives us is this limit, which we can now evaluate. Just want to make a quick mention about notation here. Notice that in every step when I'm showing how I compute my limit, I actually have the limit written with me. And the equal sign is out in front of the limit. You never write the equals in between here. That's bad style. Never write it in between the two. And the second that I actually go to do my substitution, when I plug the 2 in and things get numerical, that's when I drop the limit. So this becomes 2 minus 1 over 1 plus 1. So that gives us a value of 1/2. So be careful. Don't drop the limit from here. You have to carry it with you until you actually fill in the value of x. And always write the equal sign out in front, never inside. Those are 2 things I've noticed over the years that my students have made issues or made mistakes with. So always be careful about those things. Example number 2 says we want to evaluate this limit. So we could, whoa, this looks a little crazy. We can go ahead and try and do some factoring stuff here. Or, remember, we always try direct substitution first. And if I try direct substitution first here, I have negative 7 plus 7 squared minus 49, all divided by the value of 7. So when I go to work that out, actually there is a mistake here. This x should be a z, because z is the variable that we're using here. So pardon me for making an issue, or making a mistake there. So this is going to give us negative 7 plus 49, which is 42 up top, minus 49, all divided by 7, which I think is negative 7 over 7. Aha, and that's just negative 1. I didn't need to use any factoring. So I just put this example in here as a reminder that just because you've learned a new tool to evaluate this, don't try and use that tool all the time. Keep your head and remember that when you're going to do this, always check direct substitution first. Sometimes when the only tool we have is a hammer, we tend to see all of our problems as nails, but this one doesn't even require a nail. So let's move along now. In this case, I've got to evaluate the limit as x approaches 2/3 of this crazy expression. Okay, so let's check this out using direct substitution first. So 2 times 2/3 squared minus 7 by 2/3 plus 6 all over 10 times 2/3 squared minus 13 times 2/3 minus 3. So if we try to evaluate that, we're going to end up with a whole bunch of stuff, but what's up here doesn't really matter. The important thing is that in the denominator of this expression, we do get a 0. If you plug that in the calculator or work it out, take your time, you do get a 0 here, making this an indeterminate form. So we're going to have to try our factoring strategy. Okay, so let's eliminate all of this business here for now, just to get it out of our way. We've already proven to ourselves that this is going to require factoring, so we'll go that route instead. So let's delete that, and then we'll jump right into the factoring strategy. So we've got the limit as x approaches 2/3. In the numerator, I've got a factor, and so I see that I'm going to need a 2x and x to produce that first term. And to produce a 6 on the end, it's probably going to be a 3 and a 2. And let's make it a -3 here and a -2, and then everything is hunky-dory. Then in our denominator, I've got a factor 10x squared minus 13x minus 3. So when I go to do that, let's go with 2x and 5x. And to make a -3 on the end right here, let's try putting a -3 here and a +1. And then we'll check it. So that gives us 2x minus 15, which gives us the minus 13 we needed. And everything is okay there as well. And we can see in this case that 2x minus 3 over 2x minus 3 will cancel. And that gives us the limit as x approaches 2/3 of x minus 2 over 5x plus 1. Now we can fill in and evaluate. So we have 2/3 minus 2 over 5 times 2/3 plus 1. And the trickiest part here is simplifying the fractions. 2/3 minus 2 is going to be, let's see, 2 could be written as 4/3, right? So 6/3. 2/3 minus 6/3 is going to give us -4/3 in our numerator. And in our denominator, we've got 10/3 plus, let's see, over 3. We're going to have 3 over 3. So that gives us -4/3 divided by 13 over 3. Canceling those 3's, we have -4/13. So -4/13 is the value of this limit. Okay? Pretty straightforward once you realize just factor and cancel, plug stuff in, and hope that you can handle the fractions. I know that they give lots of people headaches, but we should be okay with that at this level. Okay, let's try this next one. We have a cubic to deal with. This looks like it's going to be a lot of fun. Okay, so for the cubic here, some of you might think, wow, if I'm going to factor a cubic function, am I going to have to employ all that stuff that we saw in Math 3200 with the integral zero theorem? Well, remember, you don't always have to do that. Sometimes you can do some group factoring. And in this case, it's exactly what we're going to be able to do. So if I take out a common factor of x squared first on my first pair and -9 on my second pair, I can see real quick that this is starting to get nice. Then in my denominator down here, I'll have 2x and x, and I've got to make a -4. So if we go with -2 here and -2 here, we might be in business, but let's double check that now. 2 times -2 is going to be -4. -2 times x is -2. That doesn't quite do it for us. We're going to have to try and fix that one and do that part again. So let's get rid of those few things we wrote there. So this denominator, we haven't quite got factored correctly yet. We'll give it one more whirl. So in order to get this one done correctly, we're going to go with, still has to be 2x and x to start. So we've got 2x, and we've got x there. And okay, if we try this with a -4 on the end here and a +1 there, then we've got 2 by -4 on the outsides to give us -8, 1 by 6 in the middle, and then that gives us our -7. So everything's okay there now. Finish the factoring in the numerator. We have the limit as x approaches 4, and we're going to have x minus 4 times x squared minus 9. And that looks good, but it's still not finished. So we've got 2x plus 1 over x minus 4 down in the basement here. And finishing things upstairs, as x approaches 4, we've got x minus 4 times x minus 3 times x plus 3 for a difference of 2 squares factoring, all over 2x plus 1 times x minus 4. The x minus 4's, they're gone, and so we can just fill in our 4 now, and so our limit becomes 4 minus 3 times 4 plus 3, all divided by 2 times 4 plus 1. So in the numerator, I get 1 here times 7 there, so that's a 7 upstairs, and downstairs I have a 9. So 7/9 is our limit. Okay, let's move along. Next is the or term question, and there are just 2 limits that you have to try to evaluate. Try direct substitution first. Probably not going to work. and then you're going to try your factoring strategy. After you get through that, you can pause the video now if you want to take a look at it, and then after you get through that, here's the solution. So there's the solution to those, and yes, they do both work out by factoring strategies, and we get answers of -2 and 1/36. Let's run through the key ideas in this section. It just says factoring can often be used as a method for us to evaluate a limit, which direct substitution produces an indeterminate form. Factoring both numerator and denominator, we cancel stuff that's causing the zero denominator, and that makes life a little bit easier. If you're having trouble with this topic, the one thing that you might want to do is go back and review some of your factoring techniques. We saw just about all of them in this section here, so be careful with those specialized ones, especially for cubics and things like if you need to factor by decomposition, doing it that way. So make sure you're keen on your factoring. We've been doing it since grade 10, so hopefully it's not too bad. So after the trouble factor has been eliminated from the expression, direct substitution will yield the correct value of the limit. Now, remember the thing about hammers and nails. Factoring is a good tool, but it is not an all-encompassing remedy for indeterminate forms of limits. We're going to have to look at a couple of other strategies as we go ahead through the rest of our review stuff. So hopefully your studying is going well. Good luck on your final exams, and maybe we'll see you in a future session.